So hello everyone. With that brief review or refresher of energy band diagrams, we're ready now to dive into the physics of how transistors operate. Now, if there is one lecture that I hope that you remember in this course, this is the one. Because if you understand the energy band view of a MOSFET, you really understand how this device works. The rest of the course is going to be talking about details and how we write a few equations to describe this qualitative understanding. But if you understand the energy band view of a MOSFET, you understand how it works. Okay, so here's our cartoon of a MOSFET. And there's a third dimension coming out of the page, but let's assume that that's uniform. That's the width of the MOSFET. There are a couple of dimensions here. We could draw an energy band diagram normal to the surface into the semiconductor depth. Or we could draw an energy band diagram in the other direction along the channel. If we do it normal to the surface, we would actually be drawing an energy band diagram similar to the first example in the previous lecture, the metal oxide semiconductor energy band diagram. We will talk quite a lot about energy band diagrams like this and about the electrostatics of these MOS capacitors later. Okay. Now, there's another dimension along the channel. We could also talk about drawing an energy band diagram from source across the channel and out the drain. That's what I want to focus on in this lecture because that will help us understand how current flows from the source across the channel and out the drain. So we're going to be drawing energy band diagrams right along the surface of this device, right at the interface between the oxide and the semiconductor in what I'm labeling the X direction. Okay, so let's do it in equilibrium. We know the Fermi levels are constant. And if I take a look at this region, I have on the left an N-type source region. If this were a uniform N-type region, I would just have an energy band diagram that looks like this, with the Fermi level up near the conduction band because there are a lot of electrons. Now, the drain is also N-type, so I would have an N-type semiconductor energy band diagram at the drain also. But the channel is a P-type semiconductor. So if I just had a P-type semiconductor, I would have an energy band diagram with the Fermi level near the valence band. Okay, now we're going to put these all together, and there's going to be transition regions, and bands are going to bend. But the Fermi level won't bend. The Fermi level will be constant because we're drawing an equilibrium energy band diagram, at least to begin with. Okay, so let's think. We have three separate semiconductors representing the source, the channel, and the drain. In equilibrium, we know the Fermi level is constant. And we know that electrostatic potential differences move the energy bands up and down. So we can see what has to happen here. We need to develop a positive potential on the source so that we pull everything down and align its Fermi level with the Fermi level in the channel. We need to develop a positive potential on the drain so that we lower all of the energies there and we bring the Fermi levels all into alignment and we have one constant Fermi level in equilibrium. So if we draw our energy band diagram, we know the Fermi level is going to be constant everywhere in equilibrium. Over in the source, we're N-type. Over in the drain, we're P-type. We're N-type in the drain as well. In the channel, we're P-type. We connect everything up so that it's smooth. And this is our equilibrium energy band diagram of this N-channel MOSFET. N-type source, N-type drain, P-type channel in the middle. Okay? All right. Now, we're going to ask ourselves the question, if we apply a gate voltage, what effect does a gate voltage have on this energy band diagram? We'll still be in equilibrium because remember, the gate electrode is separated from the semiconductor by an insulator. No current will flow. There will be no slope to the quasi-Fermi level. The semiconductor is still in equilibrium because we're not applying a voltage between the drain and the source. We're just applying a voltage to the gate and asking what happens. Well, we know that a positive gate voltage is going to increase the electrostatic potential in the channel or lower the energy in the channel. Okay, so if we take a look at this, we're going to lower the energy in the channel. So we're going to pull all of these bands down with the gate voltage. Now, an N-channel transistor, the current is carried by electrons. I really only need to worry about the conduction band. You know, there are second-order effects that people sometimes worry about. The holes can come into play. But for our purposes, we're only interested in the electrons in an N-channel device. So I'm going to dispense with showing the valence band. We'll just show the conduction band because that's what we're interested in. So here we have the conduction band versus position. Here's the N-type source. It goes way up in the P-type channel, and it comes down in the N-type drain. And then I have a gate electrode here. And we're going to apply a positive voltage to the gate electrode. The positive voltage is going to lower the energy in the channel and bring it down. Okay. So this is what the situation looks like when we have no gate voltage or a low gate voltage, no drain or source voltage. When the transistor is off, no current can flow. There is a big energy barrier that holds the electrons in the source and holds the electrons in the drain. They can't flow across the device and out to terminals. Now, if we increase the gate voltage will pull the energy down in the channel. We'll pull it way down and we'll have an energy band diagram that looks like this blue line. Okay. Now, electrons can easily now hop over this small energy barrier and flow into the channel. And electrons can hop out of the drain and flow in there. But everything is symmetric. Electrons flowing in one direction will cancel with electrons flowing in the other direction. We're still in equilibrium. No current is flowing, but now we have a lot of electrons in the P-type channel. We say that we're above threshold. We have an N-type channel in the MOSFET, but still no current is flowing. We have to apply a voltage between the drain and the source to get current to flow. Okay. All right. So let's apply a voltage there and see if we can make the current flow. Let's begin. So we will begin by applying a large gate voltage, but then we'll lower the Fermi level in the drain. We'll apply a small voltage to the drain. That small voltage pulls the Fermi level down in the drain. It pulls everything down a little bit. So now current is going to flow. I don't have a Fermi level that's constant. I have something called a quasi-Fermi level that's going to have a slope on it. I'm showing it in the source. It's pretty much where the Fermi level was. In the drain, it's where the Fermi level was, except the drain voltage pulled everything down. And in between, it would go smoothly between the two. We've pulled all of the energy bands down. So now we have a slope to the conduction band. Okay. So there's a constant electric field. There are a lot of electrons in there. Electrons will flow down the potential hill, and they'll flow from the source down the hill and out the drain, and we get a current that begins to flow. So when the drain to source voltage is greater than 0, and when the gate to source voltage is greater than the threshold voltage, so that the electrons can hop over the barrier and get into the channel, then they'll flow out the drain. Okay, so that's the current. Okay, now let's ask ourselves what happens if we apply a very large voltage to the drain and to the gate as well. So if we apply a high gate voltage, that'll pull everything down. The energy in the high gate voltage has pushed the energy in the channel way down so that we have a small barrier. Electrons can easily hop over it. If we apply a large voltage to the drain, we pull everything in the drain down. We pull the Fermi level, or now we would call it the quasi-Fermi level, down along with the conduction and valence bands. And now we have a situation where electrons can easily hop over that barrier and just flow across the channel and out the drain, and current flows. So we would call this the on state. We've applied the maximum voltage to the gate, pushed the barrier down as far as we can. We've applied the maximum voltage to the drain, pulled the drain energies way down. It's now easy for a lot of current to flow from the source to the drain. This would be the on state. Okay. So now let's remove the gate voltage and ask what would happen. If we remove the gate voltage, the energy is going to stay high. But if we keep the large drain voltage there, then we've pulled the energy down in the drain. So this would be a situation under which we would measure the off current. We've applied a large voltage to the drain, pulled the energy way down, but we've applied 0 voltage to the gate, so there is still a large energy barrier which holds the electrons in the source, and they're unable to flow out the drain. We only have a very small probability that a few of them can hop over this very large barrier and carry current out to the drain. That's the off current. And you can see why it is so small, because we have a large energy barrier that's preventing much current from flowing. Okay. So that's the basic understanding of how transistors operate. Transistors operate by manipulating potential energy barriers with the voltages on the terminals. In the linear regime, we apply a small voltage between the gate and the source. The energy in the drain is just a little bit less than the energy at the source. When we apply an increasing gate voltage and go up, we push the barrier down. The more we push the barrier down in the channel, the easier it is for electrons to hop over that barrier out of the source and flow across and out of the drain. And we get current in the linear regime this way. When we apply a large drain voltage, we're up in the saturation regime. Then we've lowered the potential energy greatly in the drain. The device is still off if we have 0 gate voltage because there's a high energy barrier there. But as we push that energy barrier down by increasing the gate voltage, we lower the barrier. Electrons can hop over the barrier and out, flow across the channel and out the drain. That's how a MOSFET works. And you can easily understand the physics of how this device operates if you think about it in terms of energy band diagrams. You can also see why the current saturates. If I pull this energy down even more by increasing the drain voltage, that's not going to do much to the current, because what's limiting the current is the probability that it hops over this little barrier at the source end. If I make the drop further, it doesn't really matter. The current limiting step is hopping over this barrier at the source end, and that's why the current saturates. Now, we can also use this energy band view to understand what Dibble is and why we gave the name of this phenomenon, why we call it drain-induced barrier lowering. We can understand that by energy band diagrams. So here's our energy band diagram. The device is off. Here's our energy band diagram if we have a low gate voltage, but we apply a large drain voltage. We pull all of the energies in the drain down. But you can see that there's going to be some tendency, depending on how we've engineered the electrostatics, the potential at the drain is going to want to try to pull this barrier down a little bit. That's not a desirable feature. We are going to try to design these transistors in a way that the height of this barrier is predominantly controlled by the voltage on the gate, and the drain can't reach through and pull down that barrier very much. But it's bound to be able to reach through and pull it down a little bit. If it pulls it down a little bit, it's a little bit easier for the electron to hop over that barrier, and that drain-induced barrier lowering then makes it easier for electrons to hop over the barrier and get out, so I'll get a little more current. That's the phenomenon of drain-induced barrier lowering. That's why the current increases a little bit in the subthreshold regime when you apply a large drain voltage. So I'll just point out, and I don't have much more to say about energy band diagrams, that these are really two-dimensional devices, or even three-dimensional devices. So we should really be drawing energy band diagrams in both the X and the Y positions at the same time. If you're interested in seeing what some of these energy band diagrams look like, you can consult this reference here. But this is basically, we are going to be talking about energy band diagrams in the normal direction to the channel, when we're looking from the gate to the gate oxide into the depths of the device, and also along this surface here, along the surface from the source across the channel and out the drain. But in reality, these energy band diagrams are two-dimensional surfaces, and it's kind of fun to have a look at these and see if you can make sense of them and figure out what they all mean. Okay, so MOSFETs are essentially, what makes a MOSFET is that it is a barrier controlled device. We control the current by controlling the height of energy barriers with terminal voltages. That's what makes the device work. Now, there are some considerations here that we have to worry about as channels get shorter and shorter. We know that electrons are quantum mechanical particles. A quantum mechanical particle doesn't have to hop over a barrier, it can tunnel through a barrier. So here are some simulations done by a colleague of mine, Mathieu Louisier, showing these are numerical simulations which treat electrons as waves. Here's the conduction band versus position for a MOSFET with a channel length of 13 nanometers. And the color here indicates the magnitude of the current. So it tells us at which energies is the current flowing. And you can see in this case that the current that flows all flows over the top of the barrier. This is the way a transistor is supposed to work. If we were to push that barrier down and make it lower, push it down with the gate voltage, we'd get more current. Okay. Now, as I make the channel length shorter, 10 nanometers, the transistor still operates pretty much the same way it's supposed to. The height of the barrier will control the magnitude of the current. If I want more current, I apply a larger gate voltage, push it down, and I get more current. But if I continue to shrink, if I shrink to 7 nanometers, you can start to see some of that current flowing underneath the barrier. That's quantum mechanical tunneling. Okay, that's going to begin to degrade the performance of the transistor. I'm going to begin to see that in the subthreshold swing. It'll degrade the subthreshold swing. If I go too far, say to a 4 nanometer channel, then you can see that the electrons don't even know that there's a barrier there. They're just tunneling completely through the barrier. It appears to be transparent to them. We can't make a good transistor if there's no barrier to current flow for the electrons. So this device would be too small to make a good transistor. So this quantum mechanical tunneling sort of sets some fundamental limits to how short we can make the channel length of a MOSFET, because it has to operate as a barrier-controlled device. All right, so let's summarize. Everything we need to know about the essence of a MOSFET is contained in energy band diagrams. They provide a qualitative understanding of how a MOSFET works. They're barrier-controlled devices. The drain current is controlled by a height of an energy barrier between the source and the channel. In a well-designed transistor, the height of that energy barrier is controlled by the gate voltage very strongly and very weakly by the drain voltage. We have a device then that has very low dibble when the drain voltage has a small effect on the height of that energy barrier. And that's what we want to see. All right, so what's next? So what's next is where in most textbooks you would see people start. We're going to write a few simple equations to describe the IV characteristics of the MOSFET. But now that we understand how the MOSFET works in terms of energy band diagrams, we'll really have a deeper understanding of what those equations mean. So I'll see you in the next lecture and we'll continue this discussion.